So 5, 2, 1, 4, 3, 6. That's 2. 1, 2, 4. Yeah, 1, 2, 4, 5, 7. 11. Okay. Kruskal's algorithm sorts the edge weights and then includes edges in order of their edge weights, smallest first, unless the inclusion of that new edge that's being considered would cause a cycle with the edges that are already selected. So I know I wrote this down last time, and I don't want to write it again, but so I've just said it, and let's do an example here, and hopefully between saying it and doing the example, that's all reminder you need. So the edge weights, consider them sorted, and so we take the smallest one into the minimum spanning tree that we're building, and then you consider the next one, next smallest, and you see whether it causes a cycle with the edges that have already been selected. Well, that's this 2, and that obviously doesn't create a cycle, so you take it. The next one that you consider in here is this 3, and its selection doesn't cause a cycle with the ones you've selected so far. Now notice that unlike Prim's algorithm, where in Prim's algorithm what you've selected is always connected. You're growing from some set of nodes always to another node that is connected to it. Here, at any given point in time, what you've selected so far could be disconnected, as we see in this example. Then the next one you take is 4 because it's the next biggest, and again, it doesn't create a cycle. Then the next one you consider is 5. But 5 would create a cycle with the ones we've taken so far. And I haven't given you a formal definition of a cycle, but it can be a cycle of any length. It doesn't have to be 4. It's not like it's just a square or a triangle. It could be a cycle is simply a set of edges which you can walk around continuously and get back to where you started. So if I put 5 in there, we would have a cycle. And so the rule for the algorithm says don't put that in there, because after all, we know we're looking for a tree. You never want a cycle in a minimum spanning tree. So 5 is not taken, and the next one we consider is 7. It doesn't create a cycle, and in this whole process, we also have a termination condition, which is that every node in the tree is now included. Or since we know exactly how many edges will be in a spanning tree, it's always 1 less than the number of nodes. The termination condition is very simple. When you have enough edges, or when you've spanned all of the nodes, then you know to stop. So that's Kruskal's algorithm by example and by verbal. Again, it's more formally in the book, and last week we wrote it down a little more completely. Okay, so why is it correct? Okay, remember the main tool that we had for thinking about correctness, and we proved this last week, was what I'm calling a lemma. The book doesn't label their statements. They just number them. I don't remember what number it was, 5.16 or something, 4.16, 4.16 or 5.16? 4? Okay. So 4.16, and it was fairly long to write out, but it basically was this. Well, I guess I'm going to write it. If an edge, UV, is the minimum weight edge across a partition of the nodes, S V minus S, so it's a partition of the nodes, then E is in every minimum spanning tree of the graph. So implicit in here is there is a graph and I'll call it G. And if edge E, which consists of nodes U and V, if that's the minimum weight edge that crosses a partition of the nodes, which I'm calling S and V minus S, so all of the nodes, that's capital V, that's the set of all nodes is capital V. So S is some subset of nodes and V minus S is the remainder. If E is the minimum weight edge that crosses that partition, then E is in every minimum spanning tree of G. Okay, now, this, what I just wrote out, is not true. Who wants to tell me why? Yeah?
The weights have to be distinct.
Yes, this is true if the weights are distinct. And the theorem, the lemma said that. Okay, so we should say assume all weights are distinct. And now this is true, but without that assumption, what I literally wrote was not true because it would not be true that it's in every minimum spanning tree. Okay, what do you think might be true, however, if this is not there? Yeah, that sounds like a good homework question, which is if you don't have this, then the theorem or the lemma here would be if E is the minimum weight edge across some partition, then E is in some minimum spanning tree of G. Okay. So that sounds like a good thing for you to try to prove in the next homework. Okay. But it's not true that it would be in every minimum spanning tree. All right. So this is our main tool for proving correctness, and we used it in Prim's algorithm, in proving the correctness of Prim's algorithm. So now I want to give you a proof Kruskal is correct, or Kruskal's algorithm finds a minimum spanning tree. And again, we're assuming distinct edge weights. So how do we prove that? Yeah, we're going to use this lemma. So we just want to argue that every time we put an edge into every time Kruskal takes an edge, selects an edge to put into the minimum spanning tree it's building, it is at that moment the minimum weight edge across some partition of the nodes, just so that this lemma can be applied. And the lemma says that if you have an edge that has this property, then it's got to be in every minimum spanning tree of G. And so as this algorithm is proceeding, when it picks an edge and that edge has this property, it must be in that minimum spanning tree because it's in every minimum spanning tree. And so the algorithm never makes a mistake in the edges it selects. The only thing left you'd have to prove for correctness is that ultimately the algorithm finds a spanning tree. Okay, so we'll do those two things. So first thing we want to prove is that when the algorithm picks an edge E to be, and that's UV, to be in the tree, E is the min weight edge across some partition S V minus S. Okay? The way to do that is this. So here's UV. Okay, I'm just remembering that the proof in the book doesn't use UV; it uses VW. Okay, but hopefully everybody can survive that change, including me. Okay, so here we're looking at this edge, and the algorithm. We're looking at the moment when the algorithm selects it. Okay, so at the moment when the algorithm selects E, let S be the set of nodes reachable from U by edges already selected. So what that means is, here we're about to put in, or we're thinking about taking, we're going to put E in. The algorithm is going to take E. It's going to select it. And there are additional edges that have already been taken. Some of them can be reached from U, and some of them cannot. And we saw that before. Initially we took the edge 1 and the edge 2 and the edge 3 that was disconnected. The 1 and 2 were connected and 3 was disconnected. And then we considered putting in this edge, and if this was U and this is V, then the nodes that are reachable from U at that point would be this node and that node. Everybody with me? The choice of U as opposed to V was arbitrary, but just looking at one end. Okay? There's some set that's reachable by what you already selected, and some set that's not reachable. Okay? So this is going to be S, and everything else is V minus S. Okay? So that's the partition, that's a particular partition of nodes. Everything that's reachable from U among edges that have already been selected, and everything else, V minus S. So what do I want to prove about that? Is that what I want to prove about that is that E is the minimum weight edge across V minus S, across that partition from S to V minus S. Okay? So I want to show that E is the min weight edge across S to V minus S. Well, first of all, is E across S to V minus S? Okay? Well, we know that U is an S. Do we know that V is not an S? Why do we know that V is not an S? Because the picture looks that way? We need a mathematical reason. Yeah?
Well, we haven't added E yet, and there's no cycles. Like if we had added E, there'd be a cycle. So V isn't reachable.
Right. Okay. So just slightly to tighten that up, we are at a point where the algorithm picks E to put in. It isn't just examining it. It's decided, yes, I'm going to put it in. Well, that means that E, together with what we've already selected, does not form a cycle. Okay. So we claim that V is not contained in S. Okay. Because if it were, then E together with the edges already picked that would form a cycle. Why? Because S is defined as those nodes that are reachable from U by some path of edges that are already picked. So it would mean something like that. Okay, you can go from U to V along edges that have already been picked. That doesn't include E because E is now being added to it. But now when you add E together with those edges that are already picked would form a cycle, which then would contradict that the algorithm is picking it. Okay? So we know that V is not an S. Would form a cycle which would contradict the fact that E has been picked. To enter. Okay? So V is not an S. Where is it? So V is contained in big V minus S. All right, so we have said then that E crosses, so E crosses from S to V minus S. Okay? Number one. Now, is there any other edge that has been picked so far at the point when we're about to pick E, the point when the algorithm does pick E to enter? Is there any other edge which crosses from S to V minus S? No. Why? Yeah, by the definition of S. S was everything that you could reach from U. Okay? And we just showed that and V minus S is everything that's not reachable from U. It's the complement of S, so it's not reachable from U. So, but if there was an edge that went from S to V minus S, that other endpoint would be an S. It's contradicting the definition of S. Yeah. Okay. So this proof. Question? Or is that just my shoes screeching? Right. Making it sound like a question. Yeah. All right. I just erased the main lemma that we need, but we all remember what it is. Okay. So I should say and by the definition of S, no picked edge before E. I'm really running out of good-sized chalk pieces. Before E crosses from S to V minus S. Again, that's just definition of S. If there was such an edge, that would contradict that S contains all of the nodes that are reachable from U. Okay. Any additional edge that goes from what I'm claiming to be S to what I'm claiming is in V minus S, well, that other endpoint should have been an S by definition. It's therefore reachable from U. Okay, so there's no edge before you pick E that crosses from S to V minus S. All right? So is E the minimum weight edge that crosses from S to V minus S? Well, it's the first one. Remember, we're looking at the edges in order of their weight. Okay? And every other edge that has cheaper weight, less weight than E, has already been examined. Okay? And if there was an edge that was cheaper than E that also crosses from what I'm claiming is S to V minus S, then again that would have contradicted the definition of S. Okay, so not only is there no edge that crosses from S to V minus S, there's no cheaper edge than E that crosses from S to V minus S, because had there been one, it should have been added. It certainly wouldn't have created a cycle, because it would have been, because up to now there's no edge that crosses from S to V minus S anyway. So these are totally disconnected. S and V minus S are disconnected. So adding an edge in couldn't create a cycle. So if there had been an edge that's cheaper than E that crosses from S to V minus S, the algorithm would have looked at it, because it's looking at the edges in order of weight, and the algorithm would have taken it because it doesn't create a cycle. But therefore, there couldn't have possibly been one, because S is defined to be all the edges that are all the nodes that are reachable from S, from U. So by definition, no picked edge before E crosses from there, and really by the same logic, moreover, and the action of the algorithm, there is no edge in G, not just in the edges that we picked, but there's no edge in G cheaper than E that crosses crosses S, V minus S. And therefore, E is the cheapest one that crosses S to V minus S. So, by lemma 4.16, E must be in every minimum spanning tree of G. So the algorithm does the right thing at every step. Yeah?
What does it say? And I'm not able to make out what that says on the board.
Oh.
Something for and the action.
And moreover, okay, I guess I said it but didn't write it. By the definition of S, again by the definition of S, but now also by the action of the algorithm. That is, the algorithm didn't pick anything that crossed from S to V minus S at this point, up to this point. So there isn't in G an edge that's cheaper than E that crosses from S to V minus S, because had there been one, the algorithm would have picked it, because that edge certainly would have been considered, and adding it would not have created a cycle, because S is connected, V minus S is disconnected from S. So you could definitely add an edge in there, and you wouldn't be creating a cycle. So there can't be any edge that's cheaper than E. And so by this lemma, E must be in every minimum spanning tree. So this says that the algorithm, Kruskal's algorithm, the K algorithm, is correct. Okay, that's correctness. Now, implementation and running time actually is more complicated than in Prim's algorithm, and the book talks a little bit about getting the same running time as Prim's algorithm. And you can read that if you like. It uses some material that's really quite elegant and beautiful, called Union Find, which I hope to talk about in the graduate version of this class, but I won't talk about it here. And so you'll just have to take it on faith, unless you want to read those pages, that you can implement Kruskal's algorithm to be as efficient as Prim's algorithm. However, even short of that, you should be able to convince yourself that Kruskal's algorithm is reasonably efficient. You should be able to come up with some time bound on Kruskal's algorithm. How much time does it take, for example? Well, we know how much time it takes to sort the edges by weight. That's just a sorting problem. If there are m edges, that's m log m, which we often call m log n. Why do we do that, by the way? If it's m log m, there are m objects, m log m, and n is the number of nodes, usually people say m log n. Okay, well, I'll just throw out the answer here is that m in this case is the number of edges. The number of edges is no more than the square of the number of nodes. Okay, because every pair of nodes could define a single edge. We don't have parallel edges. And the log of n squared is what? It's 2 times the log of n. So m log m is at most 2 m log n. Okay? And when we take big O of 2 m log n, that's the same as the big O of m log n. All right. Well, if you got that, that's fine. Otherwise, when you read in the book that the running time is m log n, or something of that type, and in this kind of context, and you don't know how do they switch from m to n when m is the number of edges in a graph? That's the answer. Okay, so implementation I'll leave to you to think about. It might make a good homework or exam type question to say, even without fancy data structures, come up with some bound and justify the running time for implementing Kruskal. Okay, so we're done with minimum spanning trees. Lots of really wonderful applications and subtle applications of minimum spanning trees that are out there, but this will form the basis of it.